So this is, we're in section 9.5. So polar coordinates, something that we're going to use polar coordinates for the rest of the unit. Polar coordinates come up quite often as you move on in math. Polar coordinates let you express, write equations for certain kinds of graphs in a much easier way than you can in what we call rectangular coordinates or normal coordinates. And they let us do lots of kinds of problems that have certain kinds of properties, certain kinds of symmetry. They let us do those problems much more easily. The polar coordinates are just another tool that let us work with problems in a slightly different way. So what we're going to do today is we'll talk about polar coordinates, what they are, how the kind of the basics of working with them. On block day we'll talk about graphing polar equations. Graphs of polar equations are kind of nice. They do some interesting things. And then the last topic in chapter 9 is using polar coordinates for conic sections. How do we write conic sections in polar coordinates? And it turns out that it's actually a lot easier than writing conic sections in rectangular coordinates. So when we are using polar coordinates, instead of an x and a y, we use an r and a theta. And since we're dealing with our r and our theta, we end up getting our trigonometry coming back. We get to see a little bit of trigonometry. So here's our point in polar coordinates. We're going to call this point, the coordinates are r and theta. Just like when we worked with the unit circle, theta is, we measure counterclockwise from this axis. In polar coordinates, we don't call this the x-axis, we call this the polar axis. Or we also call it the theta equals 0 axis. So on this axis, theta equals 0. And we call this, rather than the y-axis, this is the pi over 2 axis. So we're always referring to our angle, and r is the distance from the origin to our point, so along this segment. And we call the origin in the polar coordinate system the pole. So r is a distance from the pole to the point. And theta is, we measure counterclockwise from the polar axis. So what we're going to do is we will talk about how we plot points in polar coordinates, just to get a little bit of familiarity with them. Then we're going to talk about how we convert back and forth from polar coordinates to rectangular coordinates, to x and y, and from x and y to polar coordinates. And then we'll talk about how we convert equations, rectangular equations, x and y equations, to polar equations, and vice versa. So just get a little familiarity with using polar coordinates. So let's look at a couple of examples. For these ones, we'll start with some easy examples. We just want to plot these points. Plot 2 pi over 4. So that's a point in polar coordinates. So if I draw a little graph here, what this is telling me is this is my 0 axis, this is my pi over 2 axis. This is saying that our angle is pi over 4, so I'm going to and I'm going to say that's the point 2 pi over 4. And what we're saying is this distance from the origin, from the pole to the point, is 2 units. Tomorrow when we do some graphing when we're doing a little more graphing, when we're graphing equations, I'll give you polar graph paper, and the polar graph paper has angles marked on it, and it also gives you circles where the radius is constant. So you plot this on the point, you plot this point on the circle that has radius 2. So that would be our 0.2 pi over 4. And if we wanted to plot, just another example, 3 negative pi over 6. So that's saying we're going down, we're going clockwise. So there's my pi over 2 axis and my polar axis. So we're going clockwise by pi over 6, and we're going out. Our distance from the origin, distance from the pole, is 3 units. So the length of this segment here would be 3 units. So that would be the 0.3 negative pi over 6. One interesting thing about polar coordinates, and this should be familiar from when we talk about unit circles, polar coordinates aren't unique. So are we good with how we plot a point? Okay. Polar coordinates are not unique. So it's important to remember that. So thinking back to when we worked with unit circles, how do we get another, if we're at a specific point in polar coordinates, how can we get another point that's exactly the same point, but that we write differently? We can add 360 degrees. We can just rotate around that circle again. Then we can go either direction. So we can add any multiple of an even multiple of 2 pi. And that takes us around back to the same point. So we can say that our theta, any point in polar coordinates, is going to be the same as r, and then the way we wrote that is theta plus 2n pi. So this is an even multiple of pi. And I'm going to say plus or minus. So we can go clockwise or counterclockwise. When we deal with polar coordinates, we can also have a negative radius. So let me go back here and say, if I have a negative radius, it's just telling me to go the opposite direction. So if this were the point negative 2 pi over 4, I would rotate to pi over 4, and instead of going out this direction, I would go the opposite direction and go over to here. So I can have a negative radius, and we can represent this point as a point with a negative radius. So we could say this is or r theta plus or minus an odd multiple of pi. So if we rotate 180 degrees, but we go in the opposite direction with our radius, we get back to the same point. So this is the way we write an odd multiple of pi is 2n minus 1 pi. So this is adding an odd multiple of pi. Oh, and this should be a negative r. And we'll plot a couple points, and I'll show as we plot some more points, I'll show how we can plot a point with a negative radius. So we can rotate around the circle by 360 degrees by 2 pi radians, or we can go 180 degrees pi radians and use a negative radius and go in the opposite direction. So what if we have a point 2 pi over 3? And we want to write this in 3 other ways. So this is our point in polar coordinates. So what's the easiest one? What's the other? What's one way, the easiest way that's equivalent to this? What are we going to do with pi over 3? Add 2 pi. Add the easiest multiple of 2 pi is just have n equal 1. So pi over 3 plus 2 pi. That's going to take me around the circle once, counterclockwise. So this is 0.2. Pi over 3 plus 2 pi is 7 pi over 3. So that's the easiest one. We could also say that this is -2, and I'm going to add an odd multiple of pi. Well, the easiest odd multiple of pi is when there's just 1 pi. And that would be -2, and pi over 3 plus pi is 4 pi over 3. And if I wanted to plot this point, -2, 4 pi over 3, I'm going to go from here around 4 pi over 3 radians. So there's 4 pi over 3. And rather than going 2 units on the terminal side of this angle, I'm going to go back the opposite direction and go 2 units in the opposite direction. So that would be the point -2, 4 pi over 3. And it's in the same place as the point 2 pi over 3. So we rotate around however many radians the angle tells us, theta tells us to move, and then rather than putting our point on the terminal side of the angle, we go the opposite direction. That's what that negative tells us. Go the other direction. And what would be a third way that we could write this point? What else could we do? We could subtract 2 pi from pi over 3. So we could say 2 pi over 3 minus 2 pi. So that would be the point 2 pi over 3 minus 2 pi is -5 pi over 3. I could also add or subtract 2 pi from any of these, and I would get to the same point. I could change the sign on the radius and add or subtract pi to any of these and get to the same point. So we could write our point in lots of different ways. All right, questions there? All right. Now that we know a little bit about polar coordinates, we want to be able to convert. How do we convert from polar coordinates to rectangular coordinates, x and y, and back? So this is going to take us back to what we did with trigonometry and the unit circle. So coordinate conversion. And it's nice, we in Calculus 2 and Calculus 3, we use polar coordinates quite a bit. And you get to the point where you can start kind of thinking in polar coordinates. And when you can think and visualize things in polar coordinates, it's kind of gives you a nice different way to look at problems. It's kind of nice when that happens. All right, so let's draw our axes here for polar coordinates, and we'll talk about how we convert. So this is our pi over 2 axis, our polar axis. Here's our point in polar coordinates, r theta. And that side, that length is r. and I'm going to do just like we did when we talked about the unit circle. Yes? Oh, sorry. Pause this for a second. And so this side is y, and this side is x, and here's my theta. So we're starting with this right triangle, and I can start writing my coordinate conversions. So with this right triangle, x would be, how can I write the length, how can I write this side x in terms of r and theta? Do you remember? X has to do with the cosine, r cosine theta. X is r cosine theta. Y equals r sine theta. We can use the Pythagorean theorem on this triangle and say that r squared equals x squared plus y squared, and that's the same as saying that r equals the square root of x squared plus y squared. And we can figure out our angle, tangent theta, opposite over adjacent, y over x. So those are our conversions. And then just to connect this back to what we did right before the last test, this gives us parametric equations for x and y, and our parameters are r and theta. We have a set of parametric equations here. So these are conversions from polar to rectangular and from rectangular to polar. So lets us figure out x and y if we have r and theta, or lets us figure out r and theta if we have x and y. So let's do a little practice with converting coordinates. So we have a point in polar coordinates. So r theta equals 4, and theta is pi over 6. And we want to go to rectangular. When we go to rectangular, all we're doing is using these conversions. So x is going to be 4 cosine pi over 6. 4 times cosine pi over 6, do we remember? Pi over 6, unit circle angle. Square root of 3 over 2. So this is going to be 2 square root 3. And y is 4 sine pi over 6. So that's 4 times the sine of pi over 6 is 1/2. Is 2. So our point is 2 square root 3, 2. So that would be the point 4 pi over 6 would be 2 square root 3, 2 in rectangular coordinates, x and y. Questions there? Let's look at another one. We have negative 2 pi over 4, and we want to go to rectangular. Same thing. So x is going to be negative 2 times the cosine of pi over 4. So negative 2 times cosine of pi over 4. Do you remember that one? What is it? Negative square root of 2 over 2. This is a third quadrant angle. So we get square root of 2. And y is negative 2 sine pi over 4. And that's negative 2 times sine of 5 pi over 4. Negative square root of 2 over 2 also. Square root of 2 over square root of 2. So the point in rectangular coordinates is square root of 2, square root of 2. And if I were to plot this, just to plot this in polar coordinates, 5 pi over 4 is this angle here. So there's 5 pi over 4. And this is saying we're going in the opposite direction. So we're going 2 units in this direction. So that would be the point 2, negative 2, 5 pi over 4. And in rectangular coordinates, that's the point square root of 2, square root of 2. All right, we good with that example? Let's go the other direction. Let's say we have a point negative 1, to polar. So now we have x and y, and we want to find r and theta. So r is a square root of 1 squared plus 1 squared, square root of 2. And tangent theta is y over x, 1. What quadrant are we in? Negative 1, negative 1. Third quadrant. What angle in the third quadrant gives me a tangent of 1? Yep, here's your hint. Sine and the cosine are equal. 5 pi over 4. So the point here is square root of 2, 5 pi over 4. So negative 1 in rectangular coordinates is square root of 2, 5 pi over 4 in polar coordinates. Are we good there? Let's do one more, where we have to think a little bit more. So let's have the points 0, negative 2 to polar. This one should be easy. What is the radius here? Let me draw this point. How far away is this point from the origin? 2 units. On the negative y-axis, what is theta? Negative pi halves, or 3 pi over 2? So we could say negative pi halves. Either one of those will work. So we could say our point is 2, 3 pi over 2. We could also say 2, negative pi over 2. Either one of those would work. And we have other ways that we could write it as well. So that one was easy. If we tried to go the other way and said that we could find r by saying that the radius is the square root of x squared plus y squared, so we'd get r is the square root of 4, which gives us 2. If we did tangent theta as y over x, we'd get tangent theta is undefined. And we'd have to remember that tangent theta is undefined at 3 pi over 2. All right, questions there? Well, converting points is fun. Converting coordinates with the points, it gets more interesting when we want to convert equations. For our equation conversions, we're doing exactly what we did for our coordinate conversions. if we have a rectangular equation, and we want to convert to polar, we're just going to substitute x equals r cosine theta and y equals r sine theta and simplify. So everywhere we see an x, we write r cosine theta. Everywhere we see a y, we write r sine theta. And then sometimes we have to do some simplification. So if we have a nice rectangular equation, we just make these substitutions and simplify. Very easy. Sometimes it's a little more tricky though. Let's look at a couple that make us think a little more. Let's convert r equals 5 to rectangular. So before we do our conversion, what is the, well, if we graphed r equals 5, what is this? What would our graph be? So no matter what theta is, it does cross the polar axis. No matter what theta is, r equals 5. What is that describing? A circle with its center at the origin, with radius 5. And we know that our conversion for polar to rectangular is x squared plus y squared equals r squared. So our equation would be x squared plus y squared equals 25. So that would be our conversion. Now isn't r equals 5 a nicer equation than x squared plus y squared equals 25? Very easy to work with this compared to working with this in a lot of applications. All right, how about theta equals pi over 4? What is that equation describing? The angle is always pi over 4, no matter what r is. So what is this thing? What is it? It's a line. This is a line. Well, let's do our conversion. Tangent theta equals y over x. That's our conversion from polar to rectangular. What's a tangent of pi over 4? 1. So our equation is the line y equals x. Anywhere along the line y equals x, if I sketch a quick graph here, anywhere along the line y equals x, theta is pi over 4, or angle is pi over 4. So this describes the line y equals x. Theta equals pi over 4. So rectangular to polar is usually a fair amount easier than going the other direction. Sometimes when we go the other direction, it can get a little tricky. So let's look at a couple of those examples. Everybody good here? All right. So we want to convert r equals 2 cosine theta to rectangular. And we'll work with these a little more tomorrow. This is actually the graph of this equation is a circle radius 1 centered at 1, 0. So we're going to come up with that equation. So anybody have an idea of what we want to do here? We're going to have to simplify somehow. But what do you think, Daisy? So you're on the right track. So we know that our conversions have x equals r cosine theta and y equals r sine theta. So we want to try to get those. We want to try to do things to our equation to get that r cosine theta or r sine theta in there, because we know that we have this x equals r cosine theta and y equals r sine theta. So we want to do something to this equation so we have an r cosine theta. So what would we have to do here to get an r cosine theta in this equation? What is the r doing to the cosine? Adding, subtracting, multiplying, dividing. Multiplying. Let's multiply everything by r. That's one way to get an r cosine theta there. Multiply everything by r. Multiply both sides by r. R squared equals 2r cosine theta. Well, that looks a little better, doesn't it? R squared is what in rectangular coordinates? X squared plus y squared. That's kind of nice. And 2 times r cosine theta, 2x. I'm going to subtract 2x from both sides. X squared minus 2x plus y squared equals 0. What is that the equation of? We just had a test over this. We have an x squared and we have a y squared. The number in front of the x squared and y squared are both the same. It's a circle. We could find the center by completing the square on x, and we would see that the circle is at, the center is at 1, 0, and a radius would be 1. So this is a circle, just like I promised. All right, one more example, a little trickier this time. How about r equals, and I'm going to leave some room here because I'm going to need to do something. 1 over 1 minus cosine theta. We want to convert that to rectangle. Any ideas what we're going to do here? So Jonas says let's square both sides so we have an r squared. That's a good idea. When we square 1 minus cosine theta, we have the quantity 1 minus cosine theta squared. So we would end up with something a little more complicated, but that's a good thought to get an r squared in there. When I first look at this, I think I don't like that fraction. How can I get rid of that fraction? How about multiply both sides by 1 minus cosine theta? That looks a little better. These cancel when I multiply this. So I get, and I'm going to distribute here, r minus r cosine theta equals 1. R is, how can I rewrite r with x's and y's? Give me a hint, square root. X squared plus y squared minus r cosine theta is x equals 1. I'm going to add the x to both sides. Square root of x squared plus y squared equals 1 plus x. Now we can square both sides. I'm going to square both sides. X squared plus y squared equals 1 plus x squared. I'm going to square this out. X squared plus y squared equals x squared plus 2x plus 1. And now I can simplify a little bit. I finally get that y squared equals 2x plus 1. So what is that the equation of? What is it? Parabola. This is a parabola. And we'll work with equations. So anytime we have a polar equation that looks like this, we end up with a conic section. This one turned out to be a parabola, and we'll talk about that on Friday. When we have our polar equations in this form, we end up with a conic. So we always, when working with these, we always want to somehow get an r cosine theta, r sine theta somehow into our equation, so we can use our conversions. All right, questions on that example? Okay, I have one question for you. This one comes up, I think, in the homework a couple of times. Sine 2 theta. Do you remember how to find sine 2 theta? We had a nice identity for this. 2 sine theta cosine theta. So sometimes you'll end up with an equation that has a sine 2 theta. You want to use this identity, and then you can multiply, end up with r's in here, so you can get an x and a y. So this one comes up. This one comes up a little bit. Okay. Homework. Every other odd there, and every other even. There we go.